So hello and welcome to our channel again. So this is a second video on the statistical physics about the Boltzmann distribution. So in the first video we have derived the Boltzmann canonical distribution law, which tells us about the energy of the particle and the relation between the number of particles. So let's the quick recap of what the formula we have derived in our previous video, and the formula was Ni is equals to the A e to the power negative beta ei. Here I is the subscript which represents the ith particle. A and beta are here constants. It's a very important point to remember that A and beta, it's not B, it's beta. 1 minute. It's not B, it's beta. So A and beta are constants. So our motto of this particular video is to derive this particular constant and to derive the probability. What probability? The probability that the number of particles being in the ei energy state. So this is what we are going to derive it, because this probability term is very important to understand the different types of other statistical physics things. So let's start deriving that particular formula. So first of all, to determine the particular constants, we have to assume some things, and we are going to say that suppose that this was our system and we supplied a small heat to that system, dq heat to the system at a constant volume. And you know that in the thermodynamics, when dq heat is supplied at constant volume, it is termed as dq is equals to T into ds. So this is a particular formula. And if we have studied our previous video, DEI energy is described as summation of ith energy EI into DNI. So this is what DI represents, DE represents, and we have discussed this in our particular previous video about that fact. Suppose that we have done this. So there is a very specific relationship between the thermodynamical probability, which means W, and S. There is a very special relationship. What is S? S is the entropy, sign of entropy. So there's a very special relationship between the entropy and the thermodynamical probability, which we are going to discuss here. And the formula is this particular formula, which is S is equals to K log of W, where K is the Boltzmann constant. It's a very common constant derived in the thermodynamics, and here W, we all know that W is the thermodynamical probability. Thermodynamical probability. So this specific relationship between this. What if I take the differential of this particular equation? So by taking the differential of this particular equation, it will be like ds is equals to K, because K is a constant, differential will not act on this. It will be D log W. So this is our very important equation. So you all know that what is the differential of the log W, because we have discussed in this previous video, and I'm borrowing the equation from our previous video, that what is the value of this particular D log W. So the value of D log W is nothing, it's just K summation over I log Ni into DNI. So if you are wondering that where we have derived this particular formula, so you are going to have to watch my previous video on this particular derivation, that what is the differential of the log of thermodynamical probability. So here we have derived this, and now we have assumed that there is an equilibrium state, because all of this particular formula we have derived in this equilibrium state. So by deriving the formula in the equilibrium state, we know that in equilibrium state we have to substitute this particular formula, and you can substitute this particular formula whenever we discuss about equilibrium state, Ni. This is the value of Ni, and we are going to plug in this particular equation. So let's see what will happen if we will try to plug this here. So let's see. So it will be ds is equals to K summation over I log of A e to the power minus beta ei. This is log into DNI. So using the basic log properties, we are going to use this as ds is equals to k sigma log of a minus beta into ei into dni. So if you are wondering that how I have written this, so you know that, so I'm going to write as how I arrive this. So here you have to watch it how I derive this. So you have to know the reciprocity of log. We have separated this. Log a into b can be written as log of a plus log of b, which is e to the power negative beta into ei, and this is log e and log e will cut out, and you will left as log a minus beta into ei, and this is what we have written here. Okay, so this is very basic definition of log that you should know. I have derived it because maybe you will confuse that how I derived this. So this is the derivation. Okay, so now moving towards another thing. This is our particular equation. Now separating it, we will get k ds is equals to k sigma log a into dni minus k beta ei into dni summation. ds is equals to, here we have imagined that the number of particle is constant, so the differential will become 0, and we have discussed also this in our previous video that dni is equals to 0. It means this whole equation becomes 0, and what we are left is with the negative of k. Beta is constant and k is constant, so we are picking off from this equation as a summation of summation of ei into dni. Okay, so if you have watched my previous video, I've also written this as de is equals to, okay, let me write it in another color, you will get confused. So de is what equals to the summation of ei into dni, and I have also written this in this particular video in the upper section. You can see that. So if I substitute d in this particular equation, you will get ds is equals to k beta and summation of ei into dni, which is equals, and we can substitute as de. So we have this equation and another equation, which is ds is equals to, 1 minute, we have another equation which is de is equals to T into ds. D is the internal energy. This is the first law of thermodynamics, and we have written this in our introduction of this particular video. And as you can see that if I substituted dE by ds as T, which let's say equation number 4, so if you substitute this dE by ds in this particular equation number 1, let's see what will happen. It will be like ds by dE is equals to k beta, and ds by dE is nothing, it's 1 by T is equal to green. Okay, so let me see. So we are going to write out this particular beta. So it will be like Ni is equals to a raised to the power e negative of beta, and beta is 1 by kt, so it is equals to e by kt. So this is our value of Ni. Okay, so now the basic probability rule, that if someone asks you that what is the probability that particle is in the EI stage, in EI energy state, so how we are going to write this in the equation form? So we are going to write this as probability of the number of particles in the EI state is equals to the number of particle Ni divided by total number of particle n. Okay, so we are going to substitute this. So probability of particle in EI state is equals to the number of particle in the ith state, and it is equals to a e to the power negative ei by kt and divided by n. So now here we have to evaluate this particular thing. So we are going to substitute A by N as C. So if I substitute A by N as C, what will happen is that the probability that it is in the EI state is equals to C and e to the power negative EI by KT. Now there is a thing that the summation of the probability should be equal to 1. Yes, this is an obvious rule in the probability. So it means this summation of C e to the power negative EI divided by KT should be equal to 1. C is constant, so we can take it out from this particular thing. So C is equals to 1 divided by summation of E negative of EI divided by KT. E into I divided by KT. So now we are going to substitute this particular value of C, because this is very important in our original equation, which was probability of the particle, number of particles being in EIth energy state is equals to C e to the power negative EI divided by KT. So putting the value of C as EI, okay, so putting the value of 1 minute. First of all, writing this particular equation, EI divided by KT and divided by summation over E negative of EI divided by KT. So this is our very important formula in the statistical physics, and this is the base of the statistical physics, which discusses about the number of particles being in the EI energy state. So this is very important formula. So what we have done in this particular video is that we have derived the energy of this particular, we have derived the relationship between the energy and the number of particles in the previous video, and then we have evaluated the constants here. What are the different constants, just like the K here was beta and another constant was A. We have evaluated the constants, then we have calculated the probability, and by use of the general rule of probability we evaluated the another constant C, which arrived, and now we are here with this equation. So this was our today's video. So thank you for watching my video.